Hi, everyone. Thank you for coming to the last session today. I want to introduce our first speaker is Zed Fashena, and he is currently a research associate in the Information Technology and Systems Division at the Institute for Defense Analyses. He holds a Master of Science in Statistics from the University of Wisconsin, Madison, and a Bachelor of Arts in Economics from Carleton College. Take it away.
Hello, everyone. Thanks for coming. I will be talking about network methods for supply chain analysis today. I will first touch on the use case. I'll talk about data engineering to some extent, and then I'll move on back to the use case afterwards. So first off, it's no secret that in the modern industrial world, every aspect of our society is dependent on functioning global supply chains. And this has been well known in defense circles for quite some time. However, the recent and ongoing Russo-Ukrainian war has put this further to the top of mind, both in defense and also outside in the broader world. I have attached a few news articles here, mainstream news articles. It's a well-known issue. And any deficiencies, any gaps, any bottlenecks in the defense industrial base and supply chain more broadly can directly impact the DoD's capabilities as well. So the question of analysis here is, how can we identify any gaps or any vulnerabilities in those supply chains? So first off, we have to look at the data. And the reality is that there's no single entity that has complete visibility for the supply chain for any for military components, including critical components. And to look at this problem, we have to look at the data sources involved. Government authoritative data sources are sometimes difficult to access. The word stovepipe gets used fairly often. And in many cases, they are access is limited for a good reason, for security considerations, classification considerations, etc. And even when data sharing is possible, even within the department, there are often barriers such as limited documentation, schema incompatibilities, refresh issues. Sometimes data sources can be connected fairly well. Other times they can be connected somewhat well, and other times not at all. And this is where open and unclassified, open source, public and commercial data sources can become much more useful to fill in some of these gaps left by government data sources. Now, of course, the actual linking up of government data sources is not replaceable entirely. In many cases, these are the only data sources that exist for this subject. But because no single entity has a complete view, there must be a linkage in order to get improved visibility for the issue itself. So now I'll talk about some of these unclassified and open data sources. So we have things like contracts, subcontracts, sanctions, SEC filings, mergers and acquisitions, manufacturing facilities. The list goes on. These are just a few examples, and these are very rich data sources, very valuable data sources that can be used to fill in some of those gaps. Now, a few considerations when working with more open data is that one, refreshing data is oftentimes easier, relatively easy, sometimes trivially easy. Data which makes it more practical to perform analyses in a timely fashion. Schemas and documentations are also quite available oftentimes. But then we get into our first problem, which is that none of these data sources are actually intended for the use case we're using it for. None of these are designed for defense reviews of defense supply chains. Their user bases are different. The stakeholders are different. The application that we're using it for, which is identifying defense supply chain vulnerabilities, is not the primary use case, secondary use case. It doesn't show up at all most of the time in the use cases listed for these data sources. So there is no one data source that we can use. There's no one data source that is particularly valuable. It's only when we combine 2 or 3 or 10 data sources together that we start to find something useful. So being able to combine the data sources is key. And likewise, because we are not in a one data source, one research question environment, we can't you always find a new data source for a new research question. We'll have a set of data sources for one research question, another related research question will come up, and we have to pivot and adapt the existing data to answer this research question if possible. Oftentimes the flip side happens as well. When we are working on a particular research question, another data source becomes available, as it often does, and then we have to be able to pivot and adapt, bring that new data source into play as well. So we must be able to adapt our analyses to fit these multiple data sources. So when I talk about adaptability, I have to talk about reproducibility as well, because they go hand in hand. So what is the point of reproducibility? When we have a reproducible process, we can repeat our analyses. Ourselves or someone else can repeat our analyses, either to confirm, to corroborate, to disprove the results. But the key word in there to me is to repeat, because if you can repeat an analysis exactly the same, you can also repeat it but change something. And that's the key to adaptability here. So a couple tools that are very widely known: notebook tools, Jupyter, R Markdown, etc. We use these primarily for convenience's sake, because they let us combine code, code outputs, commentary, free text, etc., all in one file. This is very convenient, of course, but it also helps reproducibility, because by storing everything together, we can knit, combine, and there we have everything reproduced. But this only gets us part of the way there. So what about version control tools? So version control tools such as Git, for instance, so ubiquitous that it's almost universal, and we think of Git primarily as a way to allow us to collaborate in teams on development. And of course, Git does that for us. But Git is also very useful for reproducibility. So when we are using Git, we track a code base from beginning to end through a series of commits. We can track every change. We can, if necessary, rewind back to a previous commit. If we find a different, if we find a problem, we can fix it. If the fix doesn't work, we can unfix it. If we're interested in exploring a new feature, we can create a new branch of commits, work on that feature, and then if that works out, we keep the branch. We might merge it back into main, or we might prune it off, and we've done no damage to our original functionality. So Git and version control systems are great for adaptability. But that's code. What about data? As we get further into the age of machine learning and AI, data becomes every bit as important as code, because in a model, the data has just as much of an impact on the behavior of the system as the code does. So we need to be just as adaptable and just as well tracked with the data as we are with the code. So now I'll introduce data pipelines. So data pipelines are, of course, broadly used for any production level software, but they're also quite applicable for analyses as well. So I'll be talking about directed acyclic graph data pipelines, common variety. So each node, each green circle here, labeled, it represents some action, some task, some transformation. This could be running a web scraper, could be pulling from a database, could be transforming a column, renaming a column, training a model, extracting parameters from a model. Any task essentially performed on the data can be represented by one of these nodes, these tasks. So those are what the nodes are. The arrows represent dependencies. So every action has dependencies as well. B depends on A, C depends on B, E depends on C, and F depends on E. Now, this essentially, if you compare this to, let's say, a Jupyter notebook with 6 chunks of code, A, B, C, D, E, F, we run them in sequence. There's no difference, assuming everything works out just right the first time. However, where this becomes quite different is the need to adapt. So the assumption in most notebooks is that a chunk is dependent on some or all or none of the chunks preceding it. This is generally true, but of course I've seen some notebooks where that's not the case, and a chunk might depend on something later on. And so we need some way to formalize what depends on what, where these dependencies are. So by marking these out in a graph format. It's explicit what depends on what else. So we see that if there's a problem in action C, task C, we know that D can have nothing to do with it. B might have an issue there. A can only affect C through its actions on B. So we can narrow down the space of tasks, code to modify, troubleshoot, etc., by dividing this the data pipeline into a graph. Now, the name of the graph, directed acyclic graph, what does this mean? Every dependency is a one-way dependency. No two tasks depend on each other mutually. It's only one way. And there are no circles allowed. There can be no circle, endless circle of tasks running together. So what happens if we add something new? Let's say we're adding a new data source, a new transformation, something new, as we will have to incorporate new data sources. Let's say we're adding in G. By structuring the data pipeline this way, we can add in G and know that we don't have to change A or B. G can only affect the overall data through C and then E and then F. Now, where this becomes useful is especially if some of these tasks take longer than others or are more expensive than others. If A or B takes a very long time to run, it's very useful to not have to change it or rerun it when we're modifying the pipeline. So by tracking the data changes in this way, we can save time and be able to more easily adapt. Now, as for how to do this exactly, many software options exist. I'm not here to recommend one or the other. Oftentimes we have to meet data where it is, depending on, is it in the cloud? Which cloud is it? Is it local, on-prem, etc.? We might have to use different tools. The key is using the tool in the first place. I'm going to be using Luigi right now. So this is a screenshot of one of the visualization abilities for one of the pipelines. So we can see here, we have all these tasks similar to the previous diagram. And all these tasks show up as green. Good news for me, that means they ran successfully. If this were live, I would hover over these and we could see statistics about them, inputs and outputs. We can see timestamps as well. I don't think you can read the timestamps, but we can see how long everything took to run. And if anything were in fact highlighted red, we could investigate this, look into why it failed, and rerun it without rerunning the entire pipeline. So this allows us to be more proactive and adapt. So I'm going to pivot a little bit. We have been talking about how to load the data, but we also need to think about what to load the data into. So I've been talking about one kind of graph, nodes and edges, a network, and I'll be now talking about another kind of graph. And that is essentially my point, that graphs can represent so many different kinds of data. So what is a graph? It's essentially a thing, another thing, and a connection between those two things. As simple as that, subject, object, and verb. So many different types of data, concepts even, can be represented in this way. And this will become more clear in a minute because we can combine data types more easily by making their format equivalent, making their structure equivalent. So it's very beneficial storing this graph natively to facilitate this. So as an example of something that can be viewed as a graph, let's look at a contract, federal contract, acquisition contract. When you first look at it, it looks like a document. There's some legal language. There's a form, checkboxes, boxes, etc. It looks like a document, but you continue to look at it and you start to realize that the contract is a vehicle through which money flows. It starts at the funding agency. It flows through the awarding agency. That's a node, a relationship, another node right there. It goes to the prime recipient. The recipient's another node. Maybe the recipient has subcontractors, more nodes, more edges. What about, presumably, if this is an acquisition contract, the contractor is delivering something to the government. That's something else. That's another node. That's another edge. What about task orders, modifications? Pretty soon, this one contract is a whole graph. As a different example, Let's say we're looking at a particular system called Zeta. I'm obfuscating all the names because we're in an open forum. So this Zeta system, some platform, some hardware, it has a subassembly, the first row down of the orange nodes. Call this a widget. This widget has 4 components to it. One of those components has 3 subcomponents, and we go down this list of different subcomponents of the system. Now, why should we bother decomposing components like this? For an engineer putting this together, maybe it's not all that useful. But because we can decompose other types of data into graphs, when we have everything in a graph, we can combine them. So contracts can be represented as graphs. Components can be represented as graphs. We can put them together. And so now we see not only what are these pieces, but who's providing them for the system. These nodes down in purple, those represent the suppliers, the subcontractors, connected to these components through a subcontract edge. Now, let's consider what this would take if we were not using a graph. So this is pretty simple. We only have 3 kinds of nodes. But let's say we are doing this in a more table format, relational databases instead. We would need 1 table for Zeta, the programs, the top level systems. We would need another table for the components, a 3rd table for the contractors. Then all of these would have properties, columns, a primary key. Then we'd have 2 more tables for the component-to-component relationships and the component-to-contractor relationship. So already we're looking at 5 or 6 tables, all of which have primary keys, and pretty quickly running even relatively simple queries becomes a little bit complicated, even with just 3 nodes, 3 kinds of nodes. Whereas in the form of a graph, this is just another kind of node. It's just another node and another edge with another label. So we can adapt very quickly to new kinds of data. So we expand this a little more, hiding the contractors now, looking at all the major components for this one system. They expand out as follows. And then we have the subcontractors as well. Now this is just one program and a relatively small one, of course. But what if we have dozens of programs, hundreds maybe? With just a few dozen programs, the number of components goes up very quickly. We get into the thousands. We add the subcontractors, especially when we start adding the lower level components, things like screws and pins, plates, these kinds of things. The numbers blow up, and we get very, very many components, different contractors providing all these things. So once we have multiple programs, then we can start asking some questions across programs. One obvious question is, what components are shared between programs? Let's say we're looking at these 2 programs. What is shared? All these orange components are shared between these 2 programs. And this is a simple query. It is simply which components have a link to both of these programs. One query, and we can find out where these overlaps are. And I don't want to imply that these are just dots and lines on a screen. Every one of them is a vehicle for data. Every node has a list of properties, key value pairs, so we can store data about all of these things. Every component, program, contractor, we can store data in those and use that. So I'll also make it clear that these are not graphs made in PowerPoint. This is the screenshot directly from the a graph visualization tool plugged into the Neo4j graph database. Neo4j is one tool among many, but it's one that's pretty useful. So here we're looking again at the subcontractors in a component. In this case, one component has many subcontractors over different periods of time. So because we're looking at subcontracts, we can break this up. We can filter based on data about these subcontracts, looking at block orders, for instance. So we can, in this case, we're color coding the contractors on the top are suppliers for the block 1 order, the yellow suppliers on the bottom for the block 2 order, different date range, and the green present in both. So because we store the data like this, we can quite easily do these kinds of filters, queries. Now, here's another case. We again have the blue systems on top. We have the components. I'll draw my attention to the left. We have that far left component and a highlighted contractor right there. Now, this contractor is connected to another contractor. We've introduced a new edge type. That's an acquisition. So this lower left company acquired this far left company. So we've already introduced a new kind of edge here. The acquisitions, a new kind of edge, along with the subcontracts and the components. And we've also introduced a new type of node down at the bottom. So in gray, that's a country. And so the acquiring company has a location in this other country. So we've introduced a new edge and a new node, but this is quite simple. In the graph format, it's just another node, it's just another edge. We can query it the same way we can query anything else. So right here, we simply can run a query to find, well, what are the countries that have locations that are connected to one of these programs? So we can do this because we've made everything into a graph. We can find these things because we have a common language to speak for these different types of data. Here's one more example. Let's say we want to know, we looked already at components shared. What about contractors shared? So here in the middle, we have a single contractor that is providing components to these 4 different programs. Now, is this of interest to the DoD? It depends on what these components are and what these programs are, but we can find where these overlaps are by combining these data sources together in a common format. And if you have any questions, happy to answer them.
Hi, thanks for the interesting talk. I'm kind of wondering about the sort of usability of these kind of software compared to relational databases, which many people are at least familiar with. Is there a learning curve to learning how to use these graph-based software database systems? Can you just talk about that generally?
I would say yes and no, that there is a learning curve in setting them up and loading in data. It is similar, pretty similar to SQL in relational databases, but not quite the same. So there is a learning curve there. I would say that using them is quite a bit easier. There's not very much of a learning curve depending on the platform by which you interact with it. So there's the database itself, and then you can interact with it with various platforms. And some of those platforms are easier to use than others. So with the easier ones, it's very easy to interact with them. Of course, when you do more complicated queries, more complicated tasks, then there's a bit of a learning curve. So I'd say that there's, yes, a learning curve for setting them up, and there's the learning curve is very shallow for basic usage.
Anyone else here? I kind of got one. I'm curious that you use 2 different types of, or used graph databases for 2 different applications here, the pipeline and also the supply chain decomposition. Are there things that you've noticed at this workshop that are kind of ripe for using these graph networks as well? Are there things that you've thought about?
Well, one thing that jumps out is computer networks. So there's been a lot of talk about cyber and that computer networks are a natural use case for networks because they are interconnected computers, VMs, etc. So I think that that's one potential use case right there is in cyber.
Okay, thanks. Thank our speaker again.